The goal of IRIS-HEP's analysis systems focus area is to create sustainable analysis tools that will extend the physics reach of the high luminosity LHC by creating greater functionality, reducing time to insight, lowering the barrier for smaller teams, and streamlining analysis preservation, reproducibility, and reuse. Our strategy to meet this ambitious scientific goal is to leverage the developments from industry and the broader scientific software community. The LHC experiments are multi-purpose experiments, and they can be used to address a variety of scientific questions. Therefore, we need modular components that we can assemble into analysis systems to address specific scientific use cases. Let's consider a prototypical analysis workflow. Scientists will first want to collect a subset of collision events from the large multi-purpose data sets that are collected, organized, and managed by the different experiments, which are relevant for addressing their scientific question. These collision events are complicated, and they have rich, highly structured data associated to them. But when addressing a specific scientific question, physicists are usually interested in specific features of those events, which we call observables, and they can be computed from the raw data. The analysis system must be capable of efficiently selecting those events and calculating those observables for both the observed data and large simulated data sets which represent theoretical predictions. These ingredients must be brought together to form a statistical model to test those theoretical predictions, including the effect of statistical and systematic uncertainties. In addition, these analyses are subject to a variety of cross-checks, and the design of the analysis is iterative, which means that reducing time to insight is critical. Once the analysis has been completed, it's important that it's preserved to ensure reproducibility and reuse. For instance, physicists may want to be able to reinterpret an analysis to see if it puts constraints on some new theoretical model. While we take on a leadership role for many of these developments, for it to be successful and sustainable, it's important that it's a community effort. Therefore, we partner with stakeholders from across the community to develop this ecosystem of tools for future analysis systems. Now we'd like to take you on a guided tour of the analysis tools that are being developed for the Analysis Grand Challenge.
Cabinetry is a tool that physicists use to provide the high-level description of the analysis they would like to perform. In IRIS-HEP, we have embraced the use of declarative specifications. Physicists describe what they want, instead of providing the specific details of how to do it. In Cabinetry, physicists describe the event selections and observables they need, and which systematic uncertainties should be accounted for. Cabinetry then uses other tools in the IRIS-HEP ecosystem to assemble a statistical model, which can subsequently be used to test a specific hypothesis or theory.
FunkyDL provides a language for describing the event selection and defining the observables that we would like to compute. Again, we'd embrace a declarative approach, which gives us flexibility in downstream implementation.
Hi, I'm Lindsay Gray. I'm a scientist at Fermi National Accelerator Laboratory, and I'm one of the lead developers of the Coffee project. Coffee is an HEP community project collaborating with IRIS-HEP. It makes use of IRIS-HEP's uproot and awkward array libraries to provide an array-based syntax for manipulating HEP event data in an efficient way that is aligned with the style of modern data science and machine learning tools. In addition to this, Coffee is an incubator for understanding how HEP-specific software needs translate into the columnar analysis paradigm. Finally, Coffee also supplies facilities for horizontally scaling an analysis in order to reduce time to insight in a way that is largely independent of the resource the analysis is being executed on. By making use of modern big data technologies being considered for HEP analysis facilities, such as Apache Spark, Parcel, Dask, WorkQ, or IRIS-HEP's ServiceX, it is possible with Coffee to scale an HEP analysis from testing on a laptop to, for instance, a large multi-core server, computing clusters, or even supercomputers without the need to alter or otherwise adapt the analysis.
I'm going to be talking about ServiceX, which is a data extraction and delivery service which can be co-located with data sets to provide fast and efficient data reduction strategies. It extracts data from some of the large multi-purpose data sets that are written in experiment-specific data formats.
It's at this stage that the event selection and other analysis code that was specified in a declarative way is then translated into concrete instructions tied to the experiment-specific data formats and software environments. This strategy allows us to optimize this low-level data-intensive processing stage and to flexibly make changes in the implementation without directly impacting the high-level description of the physics analysis.
ServiceX can then deliver the results to services like Coffee in popular and powerful formats like awkward arrays or Parquet files. The results are cached to reduce time to insight for analysis tasks that are developed through frequent iterations. The design of ServiceX enables reproducibility in this stage of the analysis.
Data in high-energy physics is highly structured. Unlike tabular data, data in high-energy physics involves nested variable-length data structures that can be, well, awkward to work with. That's where awkward array comes in. Awkward array is a Python library that uses familiar idioms and syntax you find in modern data science tools like NumPy, but extends those to more nested and variable-length data structures encountered in HEP and other fields. And it's also fast, using vectorized low-level implementations, which is critical for scaling to large data sets.
While we process each collision event independently, understanding the data at the LHC requires a more global view. We need to study distributions of observables. We need to compare the distributions that we observe in the data to what we predict from our theories. We build these predicted distributions from synthetic datasets of simulated collisions. Of course, our simulations aren't perfect, so we also need to account for systematic uncertainties that result from possible mismodeling and miscalibration of our detectors or other effects. HistFactory defines a specification for how all of these ingredients can be brought together into a statistical model that quantifies the probability of the data given a theoretical prediction. And as the name suggests, histograms play a central role.
Histogramming is ubiquitous in high-energy physics. It is by far the most common way to visualize data and to communicate and manipulate distributions, and is a key component to many of our analyses. As a result, particle physicists are power users for histogramming libraries. We've been writing them since at least 1973. The C++ Boost library's histogram package, developed by high-energy physicist Hans Dubinsky, is one of the fastest and most feature-complete libraries for histogramming available. In close collaboration with the original author, we have developed Python bindings for Boost-Histogram, which are much faster than NumPy, provide support for composable axes types like categorical and circular axes, support multiple unthreaded fills, and provide powerful after-fill manipulations. We've built an ecosystem around this, featuring Hist, an analyst-friendly front-end with conversion and plotting tools. Our other libraries, like Uproot, support standardized protocols for maximum interoperability. As part of this work, key underlying technologies making this possible were advanced, including PyBind 11 and CI Build Wheel, which support general-purpose packages like SciPy and MyPy. The development here has enabled advancements in a lot of our other libraries as well, including Awkward One.
The analysis system translates Cabinetry's high-level description of an analysis into instructions for filling a large number of histograms. Once those histograms are filled, Cabinetry constructs a statistical model using the HistFactory specification.
PyHF is a pure Python implementation of the HistFactory specification. It supports a number of different computational backends, including NumPy, and popular machine learning frameworks like PyTorch, TensorFlow, and JAX, which can take advantage of GPUs, TPUs, and other hardware accelerators. PyHF also implements the standard statistical procedures of the field and leverages automatic differentiation to dramatically accelerate likelihood fits. We have some examples where the time to fit a statistical model is reduced from a few hours to less than 10 minutes, which dramatically reduces the time to insight.
Typically, the theories that we would like to test at the LHC, like theories of dark matter or supersymmetry, have some free parameters. That means that the predictions of the theory might depend, for example, on the mass of some new particles or how strongly they interact with the standard model. To test the theory, we need to scan over the parameters and compare those predictions to the observed data. That means that we need to create statistical models using tools like PyHF and perform statistical tests for each of these parameter points. But this can be done in parallel, and it's a perfect place to leverage the power of accelerators like TPUs and GPUs. This is the reason why we have created a fitting service that is optimized for this task. Our prototype fitting service is implemented using FuncX, and we can deploy it on high-performance computing centers.
Thanks to PyHF, we can efficiently serialize the statistical models and send them to the fitting service. And this allows us to horizontally scale this part of the analysis workflow. In our prototype, we were able to fit over 250 statistical models in just under 30 seconds, and this includes all the overhead of communicating with the service itself.
Good visualization is at the heart of, well, good science. If you think of any recent scientific discovery, like the emergence of gravitational waves or the Higgs boson, your mind is probably drawn to the image that best resembles the discovery. It's what you see in media, and it's what scientists share with other scientists. It's a really important stage of the scientific process, which is why it's really important to have good software to enable scientists to display their results in the best way. An example of a piece of software that helps us do this in high-energy physics is mplhep. It's a wrapper around the popular Pythonic plotting library matplotlib that allows for really quick access to visualization styles from the major LHC experiments, like ATLAS and CMS. And it's really good in situations like maybe you're pushing for a publication deadline, where you need really quick turnaround on good visualizations. Not only do scientists need to make good quality figures for the public and their colleagues, they also need to make good quality plots for themselves. And I'm not just talking about, pretty figures, I'm talking about diagnostic plots, metrics, things that help scientists know what's going on underneath. Having that baked into a software package is a really useful feature, and Alexander Held's Cabinetry is an example of such a package. It's responsible for driving the workflow for bin likelihood fits. And baked there into the software is the ability to view diagnostics and metrics from that fitting process, such as pull plots, ranking plots, and likelihood scans, the final metric itself, like exclusion plots. There's a whole bunch of stuff there.
Historically, publication of a result in a table or a figure marked the end of the story for an analysis. But today, we recognize this is not the end of the story. In fact, these results can be reused in a number of ways. Theorists may want to statistically combine the results of this analysis with another. They may want to reinterpret the results in the context of a different theory, and that information doesn't necessarily or naturally fit in a table or a figure on a two-dimensional piece of paper. For these reasons, we want to publish statistical models in their native form. The PyHF statistical models can be serialized in a JSON format, which is plain text, that is both fully featured and human-readable. Recently, the ATLAS experiment has started to publish these statistical models on HEP data. HEP data is the standard data repository for the field, and IRIS-HEP members are working directly with HEP data to support PyHF as a native format. This is already having an impact. Theorists are already using these published statistical models to refine our understanding of what the LHC data has to say about the universe.
Designing and executing an analysis at the LHC is time-consuming and requires a lot of effort. It is important that we get as much out of that effort as possible. One way to extend the impact of such analysis is to reuse and reinterpret them. RECAST is a framework that can make use of a preserved analysis pipeline to test new theories. But this reinterpretation is computationally expensive, because testing a new theory requires creating new synthetic datasets using physics simulators. Therefore, one wants to be smart about which theories are tested. This is when active learning comes in. Active learning algorithms can efficiently explore the parameter space for a new theory and exploit the information from already tested theories.
To sharpen our focus on the goals of IRIS-HEP and to aid in integrating the different components of an analysis system, we've created the Analysis Grand Challenge. The Analysis Grand Challenge comprise a vertical slice of representative LHC analysis, pieces of which we have just described. The scope of the challenge includes the design, execution, and the reinterpretation stage.
In addition to software aspects of the problem, the challenge also includes the deployment of these software solutions on analysis facilities. It is actually the realization of the software component on facilities that make an analysis system. Even though the exact software used in Halloumi LHC era is still not clear, we need facilities at least for quickly prototyping of our services. Coffea-casea is one of the prototypes of such analysis facility. It is easily scalable, provides user-friendly computations environment, such as Jupyter and Dask, that simplify, facilitate, and accelerate the delivery of high-energy physics results. The facility is built on top of multi-tenant Kubernetes cluster and integrates with additional dedicated resources allocated via fair share through the local HT Condor system. In addition to user-facing interfaces, facility also manages access control through single sign-on and authentication and authorization for data access to modern data delivery services.
IRIS-HEP has a robust training program, and we are active in several community building activities. We know that training is central to building the community skills needed to address the computing challenges of the HL-LHC area. As we deploy and refine the prototype analysis systems that we are developing for the HL-LHC, we are ramping up our training efforts in this area as well, and we are very much looking forward to the feedback that we will receive.